So this video is for the paper 1 questions on 9.3 interference, paper 1 being multiple choice. QBank found 17 questions, and this solution video is for the majority of them, but some have been set aside for a take-home assessment. At any rate, so number one's kind of interesting, and it references a diffraction grating and a prism. So actually for the prism, you'll need to remember refraction, which is topic 4.4. I see the Snell's law relationship in 4.4, and so that's what the prism is getting at. Then we have the diffraction grating over on the right. So let's first talk about the prism. We hopefully remember that by dispersion, red changes direction. It refracts the least. It has the smallest relative index of the visible light colors, and violet refracts the most. So in terms of the direction change, we would have Roy-G-Biv looking like so. And so M would be red, and then N would be violet on the other side of the spectrum. But the diffraction grating actually is kind of the other way around. The longer wavelength has the greatest change in direction, I guess if you wanted to look at it that way, and the shorter wavelength has a smaller change in direction. And we know this based on n lambda equals d sine theta. So as lambda increases, being the red end of the visible light spectrum, sine theta increases, and so the angle away from the center line also increases. Apologies for my seemingly wobbly handwriting tonight. I don't really know what's happening there. That's like a D. But at any rate, so the Roy-G-Biv setup for the diffraction grating is also Roy-G-Biv conveniently, meaning that P will also be red and that Q will be violet. We know that for single slit and multi-slit, the interference pattern, or the pattern that shows up on the screen, is tighter for shorter wavelengths and wider for longer wavelengths. But at any rate, both M and P are going to be red, and that leaves us with choice A. Okay, next question. So here we have number 2. Monochromatic light of wavelength lambda is insolent normally in a thin liquid film of index N that's suspended in air. It's air on both sides. The rays are shown at an angle to the normal for clarity, although we know that the rays are actually coming in normal to the boundary. But anyway, what's the minimum thickness of the film so that the reflected light undergoes constructive interference? Well, let's look up the formula for the condition for constructive interference in a thin film. Now, the data booklet equations are set up for the arrangement that they have here, where you have small index to begin with, big index in the middle, and then small index again on the other side. The boundaries are vertical instead of horizontal, but that doesn't change anything, of course. And this asks for the minimum thickness, and I had said earlier that M is an integral number, starting with 1, but actually M could start with 0, because the minimum thickness actually relates to 1/2 lambda, not 1.5 lambda. So we'll let M be 0 for the minimum thickness. And the problem just says that the wavelength is lambda, and that we don't actually know the index N of the film, so we'll just call that N. And D is the thickness of the film, so it asks what is the minimum thickness of the film, so that we are solving now for D. And so we divide both sides by 2n to get D alone, and of course 1/2 divided by 2 is 1/4, so that gives us that the minimum thickness is D is equal to lambda over 4n. And that is choice A, lambda over 4n. All right, next question. Okay, so number 3, we have 2 diffraction gratings x and y. It says that y has more lines per meter than x. Now the formula for diffraction gratings is d sine theta equals n lambda, where d is the distance between the slits. More lines per meter. If you're fitting more lines per meter, that means that you have a smaller d being like the distance between the slits. So y with a greater number of lines per meter is going to have a smaller d than x does. So that right there means that statement 1, adjacent slits in the gratings are further apart for x than for y. That is true. So we need to have 1 in the set. So it is not choice C. It has to be A, B, or D. Then we have statement 2, angle between red and blue light in a spectral order is greater in x than for y. Well, the difference in red and blue light, red has a longer wavelength than blue does. And actually, come to think of it as I read the question, while that's true about red and blue light, it's actually comparing x and y. So it actually has more to do with the slit separation than it does with the wavelength of red and blue light. And so looking at slit separation, for any given wavelength, red or blue, x has a larger slit separation, a bigger d. And so I can see that d and sine theta are inversely proportional, so that for any given n lambda, n just being an integral number, so for any given wavelength with a larger slit separation d, I'm going to have a smaller sine theta. And of course, sine theta varies with theta, not linearly because it's a sinusoidal function, but as theta increases, sine theta increases. As theta decreases, sine theta decreases. So for a larger slit separation, you are going to get a tighter angle. And so the fringes on your interference pattern are going to be tighter for a larger slit separation. And so 2 says the angle between red and blue light in a spectral order is greater in x than in y. That is not true. X with a larger slit separation has a tighter angle, and so 2 is not true. And so by process of elimination, that leaves us with choice B. But let's take a look at choice 3, and we'll see why 3 is true. This is the number of visible orders. How do we figure that out? And this is actually where n comes in. N is the order of the light, and so it's kind of like, what is the maximum n? So as the angle increases, for any given slit width and wavelength, as the angle increases, n also increases. But 90 degrees is the maximum. 90 degrees away from the center line is not going to hit the screen at all. So if we put in sine of 90, the sine of 90 degrees is 1, and so the maximum n count, the maximum number of orders that you can see, or that basically like just beyond what you can actually see, is given by d equals n lambda. And so x has a larger slit width, and so x with a larger d, larger slit width, is going to yield more orders that you can see on the screen. And so yes, choice 3 is in fact true. The total number of visible orders is greater for x than it is for y. I kind of ran out of room a little bit, so let me zoom in on what this is trying to say here. And so more orders actually means that is a larger n, like the number of orders you can see, and fewer orders would be a smaller n count, because we can see that d and n are directly proportional. Speaking of diffraction grating, let's look at number 4. So it says the light of wavelength lambda is normally incident on a diffraction grating of spacing 3 lambda. What is the angle between the two second order maxima? Alright, it says that d is 3 lambda. And we're talking about the second order maxima, so n would be 2 in this case. And we're trying to solve for theta, so divide both sides by 3 lambda. Alright, and if we solve for theta, we get theta is arc sine to the negative 1 of 2/3. Choice A. Wrong. Not choice A, it's choice C, because they love to pull these tricky questions. Reread the question. What is the angle between the two second order maxima? Theta is the angle of the second order maxima, like of either second order maxima from the center line to that maximum. Let me draw a little picture to show you what I mean. So we're going from the grating to the screen, and so we have, of course, the fringes that occur. We have the central maximum, 0, and then we have 1, 2, 3, 4, etc. 1, 2, 3, 4, and then we have one on the other side, 1, 2, 3, 4, these other maxima, first order, second order, third order, fourth order, etc. And so theta, in this case that we just solved for, to the second order maximum is this angle right here. But it says, what is the angle between the two second order maxima? So it's not just that one maximum, it's the other one as well, and it wants the angle between those two maxima. So theta that we solved for is sine to the negative 1 of 2/3, but we want to double that to get from one second order maximum to the other one. So it is 2 sine to the negative 1 of 2/3. So that is choice C. Tricky, tricky, tricky. Next. Also, apologies for my Apple Pencil that sometimes wants to write with a thin line and sometimes wants to write with a thick line, depending on the zoom level. I bet it doesn't bother anybody but me, but it bothers me. If it bothers you too, apologies. All right, number 8. Wait, not number 8. I just did number 4. I was about to say, that went quick. Here we go. Number 5 is over here. Number 5, Young's double slit. All right, 2 slit, let's go. So even though Young's double slit experiment is in topic 9, 2 slit, double slit interference patterns, the formula for that was actually covered in 4.4, where D is the distance from the screen to the slits, it's capital D. S is the distance between the fringes on the screen, and then lowercase d is the distance between the slits, which at least is consistent with the equation for diffraction grating, where lowercase d is also the distance between the slits. I guess one way of thinking of this equation is that S stands for screen. I don't think that's what that means, but maybe that'll help you remember it. But anyway, so S is lambda d over d. Let's get back to the question. And it says that the distance between the fringes, that would be lowercase s, because it's on the screen, is too small to be observed. So I want to increase s. Now, increasing the frequency of light, increasing frequency would, because of v equals f lambda, would decrease the wavelength of the light. Decreasing the wavelength would actually decrease the distance between the fringes, so not A. Then increase the distance between the slits. If I increase D, I can see that D and S are inversely proportional, so increasing D would decrease S. That's not something that I want to do. I want to increase S so that I can see it. Increasing distance from slits to screen, that is big D, the capital D, and I should say capital D. So by increasing capital D, I increase S. That seems to be a good thing. I can see that they are directly proportional. So increasing the distance to the screen is going to increase S. So C is for sure a viable choice. And then D, increasing distance between the light source and the slits, that has no bearing on the equation. So not D, that leaves us with C. I don't know, sometimes they give like a little like field there. They give you a lot of space to write a letter C there. Use that space. So there we go. Alrighty, next question. Transparent liquid film with refractive index 1.5 coats the outside of a glass lens of higher refractive index. The liquid film is used to eliminate reflections from the lens at a wavelength lambda in air. What's the minimum thickness of the liquid film coating and the phase change at the liquid glass interface? All right, so we remember that when you put a thin film on a higher index than the equations in the data booklet for constructive and destructive interference are reversed. I'm looking at the reference table. Yeah, 9.3, those constructive and destructive equations, the 2DN equations are flipped. I'm just going to write that down as a note. Okay, so we're looking for the coating thickness and we're looking for the phase change. I think the phase change is easier to answer. So let's break down how that is going to work. Let's see, I'm going to draw it beneath the answer spot. All right, so we're going from air with an index of 1 to the thin film and then read to glass, which has a higher index. So here are the rays. Remembering that when light transmits from one medium to another, there is no phase change, but when light reflects off of material of higher index, there is a 180 degree or pi radians phase change. And so air off the thin film, that reflection is phase shifted 180 degrees, and within the thin film, that reflection off of the glass is also phase shifted 180 degrees or pi radians. So it's asking specifically about the phase change at the liquid-glass interface. That is going to be pi radians phase change, so that eliminates choices A and C. And then it wants to know what is the coating thickness. So let's see. We want a destructive interference because we're trying to kill the reflection, right? Minimum thickness. Eliminate reflection. Yes, we're looking for a destructive interference condition. So referring to the data booklet for destructive interference, but it's not what the data booklet says. I'm actually using the constructive interference because the equations switch. So destructive interference is 2dn equals m lambda. No, it doesn't, because as I said, once again, they switch because I'm on glass. So that's 2dn equals m plus 1/2. M plus 1/2 lambda. And the minimum thickness would just be 1/2 with an m of 0. And it says that the liquid film has an index of 1.5, and we're trying to solve for d. So 2d 3/2 equals lambda over 2, so then that half there and that 2 get eliminated. That gets me 3d equals lambda over 2, therefore d is lambda over 6. So that's lambda over 6 coating thickness with a phase change of pi radians, choice D. All right, next question. Wait, we have to use the maximum area. D. We'll call that capital D. Yep. 7, let's see. All right. Graph shows variation with diffraction angle of the intensity of light when monochromatic light is incident on 4 slits. So we have 4-slit, multi-slit interference pattern here. Number of slits has increased, keeping the width and separation of these slits unchanged. Right, so this question, the formula, I can write down the formula. It's n lambda. I don't even care that it's thick. It doesn't even really matter. N lambda equals d sine theta. But one thing to recall with multi-slit diffraction patterns, as the number of slits increases, so as you increase the number of slits, there's more light coming through, so the intensity increases. Each maximum gets tighter, gets narrower, but the actual position of the maxima, the actual theta, does not change. Now, don't read too deeply into this. Don't be like, no, wait a minute. If I increase the number of slits, wouldn't that have more slits per unit distance, like a greater slit count if we're thinking diffraction gratings? And so a greater slit count would mean a tighter slit separation. But this isn't like a diffraction grating with a fixed grating size. This is just like if you have a screen and you just increase the number of slits. And so actually the quote-unquote grating size would increase because we're just adding slits. We are not changing D, the distance between the slits. So yeah, that's we write that in as number of slits increases. We write in no change in D. We're not changing that. So yeah, intensity goes up, each maximum does get narrower, and the actual angle doesn't change. So, possible changes to the pattern. 1. Separation of the primary maxima increases. That's making reference to the angle, the actual angular position of the maxima. That is not true. So not 1. Intensity of the primary maxima increases. Yes, intensity does go up. So 2 is true. 3. The width of the primary maxima decreases, that they get tighter or narrower. Yes, that's also true. And so is 2 and 3 a choice? Yes, C. And so 7 is choice C. I think I'm going to make this answer key for 1 to 13 and then reserve 14 through 17. That's a quarter of the multiple choice problems. Anyway, so number 8. So this is interesting. We have a diffraction grating. The formula for diffraction grating is n lambda equals d sine theta, where n is the order of the maximum they're referring to. And we have two angles here, alpha and beta. Beta is the angle to the second order from the center line, from the 0 order. And then alpha is the angle from the first order to the second order. That's interesting. So what's the expression for the wavelength of light used? Well, let's start with beta, because beta is measured. We normally measure our angles from the center line, the 0 order, so let's start there. And that's second order, so 2 lambda equals d sine beta, and we're solving for wavelength. And I seem to have stumbled on the answer. Lambda is d sine beta over 2, choice B. I'm still curious about alpha, though. I was going to solve for alpha in terms of the expression for the second order with beta, and for the first order, which the angle would be beta minus alpha, and then trying to get an expression for alpha. I just don't see this worth the time, honestly. It's a multiple choice question, and lambda is d sine beta over 2. So anyway, as much as I want to deep dive on 8, we have better things to do, like number 9. Okay, number 9, thin film question. It says it's surrounded by air, so I'm assuming that it's on both sides. Top and bottom is air, so then the data booklet equations don't need to be flipped. They are good as they are. It says the intensity of the reflected light is at a minimum. So at a minimum tells me destructive interference. Here's our equation for destructive interference. 2dn equals m lambda. Solving for d, that gives us m lambda over 2n. Of course, if m were 0, then that would mean that the thickness of the film was 0, and then you wouldn't have any film. So we have to start with m equals 1, so that it says a possible thickness of the film. So in order to satisfy this condition, the film could be lambda over 2n thick, could be lambda over n thick, could be 3 lambda over 2n thick. So let's see what we have. I can see that lambda over n is a possible answer. And I have 1/4, that's not a thing. 3/4 is not a thing. 5/4 doesn't seem to be a thing. It's either 1/2, 1, 3/2, 2, etc. So in any case, I can see that lambda over n does satisfy the condition, so C is our answer. Alright, so on this page we have 10, 11, and 12, so let's take a look at number 10. Monochromatic light incident on 4 rectangular parallel slits. First principal maximum is observed at an angle theta to the direction of the incident light. Again, the way it's like, well, why would the first one be observed at an angle? Because the central maximum is the 0th, I guess you could say, maximum. So the first maximum would be on either, first maxima would be on either side of the central maximum. Anyway, first maximum is at an angle theta to the direction of the incident light. Number of slits is increased to 8, each with the same width and spacing as the first 4. What is true? So we already saw in number 7 how as you increase the number of slits, it lets more light through, and so the intensity of each maximum is going to get brighter because there's more light there. So 2 has to be there. So that eliminates choice B. Let's take a look at the other choices. The angle at which the observation occurs is greater than theta. Man, this is shenanigans. They recycled this question. Number 10 is pretty much exactly the same as number 7. And number 7, they gave you like a little diagram, but the principles of the question are the same. As I increase my number of slits, forget about statement 2, seed number 7, this whole flippin' question. C number 7. But as I increase the number of slits, there's more light coming through, so the intensity is going to increase. Each maximum seen is going to get tighter, it's going to get narrower, so the width decreases, but it does not change the angular position of each maximum, so definitely not 1, so not 1, but 2 is true and 3 is true, giving us choice C. I believe that number 7 also had an answer of choice C. So, I mean, give me a break. At least get creative with your answer choices. But so, yeah, that's a freebie. That's a repeat, pretty much, of number 7. I guess if you didn't realize that and thought that the diagram in number 7 changed the question, it might throw you off a little bit, but it's pretty much the same question. All right, enough yapping about that. Let's get to number 11. Number 11, we have ourselves a diffraction grating. And the equation for diffraction grating in the data booklet is n lambda is d sine theta. My pencil has reverted to thick again. I think there's a certain zoom level when the pencil doesn't... Yeah, there you go. Isn't that interesting? All right, whatever. It's still legible. So we have monochromatic light incident on a diffraction grating n. N lines per unit length. The angle between the first orders is theta 1. So then we know that, the first order, that means that n would be 1. And theta in the equation is the angular displacement of the maximum from center line, and the angle in the problem is the angle between the two first orders. So the angle given is double the angle in the equation. So theta in n lambda equals d sine theta is theta 1 as featured in the problem divided by 2. They're asking about lambda. Let me zoom in a little to get a little, there we go. So lambda, and then n we said was equal to 1, so that really just gives us that lambda is d sine of theta 1 over 2. Now d is the spacing between the lines, and it says that it has n lines per unit length, and so you might remember that trick that the number of lines per unit length is 1 over the length per line, which would be d. They are inverses of each other. And so I can, instead of d, I can put in 1 over n, giving me a wavelength of sine theta 1 over 2 over n. That's choice D. Let me cheat and check the mark scheme. 11 is, you got it, choice D. Well, hopefully you got it. I got it, but hopefully I would get it, because I'm the one teaching it. I don't always get it. Not 100% of the time. I don't know anybody that has gotten every single available point on an IB exam. That's why you don't need to get every available point in order to score a 7 out of 7. Because sometimes I misread the question, just like anybody. Because everybody makes careless mistakes. That's what makes them careless mistakes. We always have to be careful. I also don't know, I can't remember the last time anybody at Southside at any level has gotten a 100 on the physics regents. High 90s, even 99s occur, but there's always one little slip. But hey, that's fine. It's like, in order to do really well, you don't have to get hundreds on everything. Am I right? Anyway, let's keep going with number 12. I think I'm going to do 12 and 13 and leave the rest as an exercise to the reader, as they say. Ooh, 12 is very interesting. We're going from 2 slits to 1 slit. And it says, what is going to change, what change will occur to the pattern observed on the screen. So yeah, 12 is actually A. Fewer maxima are going to be observed. But when you have a two-slit, you have to remember what a two-slit interference pattern looks like and why it looks the way it does. So let's zoom in a little bit here. So there's our single slit pattern. I actually had to just draw that about 5 times. That was a little bit of a challenge. But there it is. So single slit pattern, diffraction pattern. But then remember that that's the envelope for the double slit pattern. And so the double slit pattern is going to fit within that. The double slit, I should say, interference pattern is going to be modified. What's the word I'm looking for? Not modified. Encapsulated. That is definitely not the right word. Anyway, it's going to fit within, how's that? The single slit envelope. And so that blue pattern would be if you had double slit. Of course, you wouldn't actually see the black line. That's just the envelope. You would actually see the blue pattern, but of course you would see it as kind of like, if there was an actual screen, it would kind of look kind of like this. If you were, looking dead on at a screen. Bright, not so bright. Bright, not as bright. It would kind of look like that kind of pattern. But anyway, so if you were to cover one of the slits so that we no longer had a double slit pattern, but a single slit pattern, it would go from what you see there with the multiple fringes there to just the envelope, the kind of wide central band, and then 2 side bands over on the side, maybe another second order maximum even further to the side, but really not much there. So let's go back to the question. It said if you covered one of the slits and go from double slit to single slit, what happens? The intensity would increase. That's not a thing. You would increase the intensity if you let more light through. We're letting less light through, so definitely not B. The outer maxima would become narrower. No, we actually go from the pattern, the double slit pattern of multiple maxima seen to just the envelope that is kind of like the bands that you see are fewer than if you were just to have the double slit pattern. So definitely not outer maxima, narrower. And then the width of the central maximum would decrease, would get tighter. Not so. As you increase the number of slits, then the width of each maximum gets tighter, gets narrower. As you decrease the number of slits, they actually get wider. So definitely not that. But fewer maxima would be observed. Yeah, for sure. If you took away that second slit, you go from the blue double slit pattern I just drew to just seeing the envelope caused by single slit diffraction. Fewer maxima absolutely would be observed, and so 12 is A. And so we go from 12 to number 13 over here, and then I'm going to leave 14, 15, 16, and 17 for you guys. And I will record solutions for those as well after the fact. All right, 13. So 13 is interesting because it talks about multiple reflections. And I don't know that we discussed that in class, but we did discuss what happens, the underlying principle, that when you reflect off of a higher index, so let's write this down. When you reflect off a higher index, there's a pi radians full half cycle phase change. If you transmit between 2 different media, there's no phase change. And so looking at I reflects from air off of the film that's reflecting off of a higher index. So J definitely has a phase change of pi radians. Of course, J is in every answer choice. Thanks a lot, guys. So that doesn't eliminate anything. But then as I transmits from air into the film, there's no phase change. And then on the bottom of the film is air. From film reflecting off of air is a lower index. There will be no phase change. then ray K is what happens when the ray transmits from film back out into air. Transmission, no phase change. So K has not phase changed. And then L is the same business. We have a reflection off of the film air interface, but we're reflecting off of air that is a lower index. So in the only time there's a phase change is when you reflect off of a higher index, and then the only time that happens is when I reflects off the air film boundary and creates ray J. So J is phase changed. The rest of them, K and L, are not. So J only is the answer, A. Okay, so like I said, I would create a solution video for the first 13. I will create a video for 14, 15, 16, and 17 in a second video, but that is the deal with that, and I'll leave you with that. And the next video will be 9.3 paper 2 questions. Thank you.